Okay guys, so welcome back to CS307 Computer Networks. We are discussing section 4.4 from chapter number 4. This is the second part of section 4.4. In the first section, or in the first part of section 4.4, we covered IP addressing, IP header format and subnetting. In this particular lecture, or in this particular video, we are specifically going to look at how we actually assign IP addresses to host computers or to host interfaces. So the primary mechanism, or let's say the main mechanism that we use for automatic assignment of IP addresses to computer interfaces or end system interfaces or any interface that belongs to a router is via the use of something called DHCP, or Dynamic Host Configuration Protocol. Primarily, DHCP is used to assign IP addresses to interfaces connected to end systems such as servers or computers or mobile phones. It is very rare that we use DHCP for automatic assignment of IP addresses to the interfaces of a router. However, under certain circumstances, that is also possible. So, IP addresses, how to get one? How does a host, okay, or an end system get an IP address? Usually this is hard coded by the system administrator in a file, okay. In Windows environment, you can look up control panel, network configuration, TCP IP, and open up TCP IP properties to actually view the IP address assigned to that particular interface on that particular end system. In Unix based systems, it is usually in the etc folder under rc.config file, okay. So this kind of assignment is usually hard coded, okay. There is another way of automatically filling up the configuration in both of these systems, in Windows as well as Unix, and for that we have something called DHCP, which stands for Dynamic Host Configuration Protocol. It is dynamic, which basically means that dynamically we can get an IP address from a server. The server is running DHCP software, or it is called a DHCP server. So this is relatively simple as compared to basically typing in the IP configuration yourself, or the network administrator or system administrator doing it. We call this option plug and play, because all you need to do is connect your computer to the existing network and it will automatically get an IP address from the DHCP server based on that network. Okay. So a bit more detail regarding DHCP. What is the goal? The goal is to allow the host to dynamically obtain its IP address from the network server when it joins the network. Now when we say that the host is to dynamically obtain its IP address, we basically mean that that particular interface on the host that is connected to the network, okay. So host can have multiple different interfaces. It can have Wi-Fi, it can have Ethernet cable, it can have Bluetooth as well. So depending on the interface that is connecting to the network and the availability of a DHCP on the respective network, that interface is going to automatically get an IP address, okay. Once we assign the IP address, we call it that the IP address has been leased, okay, or it has been basically given to this particular interface, okay. We can renew the lease. Usually the lease is for 24 hours. That is, once a DHCP server gives an IP address to an interface, the IP address remains the same for that particular system for the next 24 hours. This is called leasing the IP address to that particular interface by the DHCP server. Now after 24 hours, the system or the DHCP server, or let's say the host, is automatically going to renew the lease once again. When you renew the lease, you have the option, or sometimes you have the same IP address. Sometimes if the IP address for whatever reason, maintenance or reconfiguration is okay. Otherwise you can just renew the existing lease. You can keep on using the same IP address, okay. So this allows the reuse of addresses, okay. Only those addresses which are basically let's say assigned to the actual interfaces which are in an on state are used, and the rest of the IP addresses available within the range that is available are still to be used, okay. They can still be assigned. So once an interface comes up, once an end system comes up, it boots up, the operating system is up and running, then it is going to ask for the DHCP server for an IP address. If the system is switched off, that means that the interface is also switched off. Under those circumstances, it is not going to ask the DHCP server for an IP address. So basically only those systems which are in an on state are getting the IP addresses from the DHCP server, and the rest of the IP addresses are still conserved. Okay. It also has built-in support for mobile users who want to join the network. Okay, more on this in a little bit. So just a brief overview of DHCP again. The working principle is that the host, the end system, broadcasts a DHCP discover message. Okay, that I need an IP address, or I will need an IP address in future. Who is the DHCP server on this network? The DHCP server responds with a DHCP offer that I am the DHCP server. Okay. After that, the host requests that can you please give me an IP address. That is called a DHCP request. And the DHCP server in response sends an IP address which is called a DHCP acknowledgement message. So simple 4-step process. First 2 steps are regarding discovery of the DHCP server on the relevant network. The remaining 2 are obtaining an IP address from that DHCP server. Okay. First 2 are optional, the DHCP discover and DHCP offer. So sometimes the DHCP server is hard coded, or the IP address of the DHCP server is hard coded in the end system. So it automatically knows that this is the IP address of my DHCP server. So it does not need to send a broadcast message to discover who is the DHCP server on this network. Okay, which leaves us with the last 2, which is basically just requesting your own IP address from the DHCP server, and the DHCP server replying with a DHCP acknowledgement message which carries the IP address that the DHCP server has released to your system. Okay. So this is a much more graphical view of the previous example. So you have one DHCP server, you have 3 different networks or sub-networks assigned to this router, 3 of the router's interfaces, and each one of them is branched out to the different computers on that network. If you look at the right side, then the IP address that is used is 223.1.2.0. That is the subnet with a /24 subnet mask. Okay, so you only have 2 laptops on this particular segment of the network. We have 223.1.2.1 and 223.1.2.2. Now let's suppose that you connect an additional laptop onto this system. Once you connect the additional laptop, then it will also need an IP address. So the arriving system is going to be acting like a DHCP client, okay, for the DHCP server which is already present on the network. So once it connects to this particular network, it is going to go through the 4-step cycle that we have discussed previously. That the host is going to broadcast or ask who is the DHCP server, and this DHCP server is going to reply to this new incoming laptop, say I am the DHCP server. Okay. Then the laptop is going to ask for an IP address for its interface which is connecting to this particular network, and the DHCP server is going to furnish it with an IP address which can be something like 223.1.2.3, okay, or something similar. This is the actual 4-step scenario. Okay, so first of all, you have your DHCP server on 223.1.2.5. You have an incoming client. The client, as soon as it connects to the network, says or sends out a broadcast. Okay, broadcast basically means that the packet is delivered to all the systems on that network or on that subnetwork. Okay, and the broadcast is asking this question: is there a DHCP server out there? Okay. The DHCP server listens to this incoming broadcast and says, yes, I am a DHCP server. Here is an IP address that you can use. Okay. And then the broadcast is to everyone, okay, that I am going to use this particular IP address, so that all the other systems on that network are aware of the fact that this IP address is now assigned to this particular client, so that whenever somebody wants to communicate with this client, they can do so. They know that this particular system is now available, okay, and it is connected to this IP address. And then the DHCP server sends back an acknowledgement, which is again a broadcast saying, okay, everyone, this is the IP address that I have given to this particular client, and you can go ahead and use this IP address. Okay, so a bit more detail. First of all, a broadcast: is there a DHCP server? DHCP server replies with a DHCP offer, saying, yes, I am a DHCP server and here is an IP address that you can use. Okay, the client acknowledges it and sends out another broadcast, okay, that says, yes, I am taking that IP address. so that the DHCP server as well as all the other computers on that network are aware of the fact that this IP address has been assigned or it is going to be taken up by this computer. And then there is a DHCP acknowledgement, again a broadcast by the server announcing to everyone that this particular IP address is now belong to this particular end system or the interface on that particular end system. Okay. And you can see that the lifetime of the message is around 3600 seconds. Okay. So basically you are free within that particular time frame to respond to the actual broadcast. Okay. 3600 seconds in total. Okay. And this is the default option. You can reduce it and you can increase it as well. Okay. And the broadcast is valid for the next 3600 seconds, so that whenever the system comes up or if it is fluctuating or there are network issues, as soon as it obtains the message, it basically replies, and that is the lifetime or the duration of the broadcast for which it is live. The request is still active. The offer, the request, as well as the acknowledgement. Okay. Moving on with DHCP, it is more than IP addresses. DHCP can return more than just the allocated IP address on the subnet. So in addition to IP subnet, it also gives you some additional information or facilitates or gives this information to the client so that it can communicate outside the network as well. Okay. First of all, it also gives the address of the first hop router for the client. Okay. This first hop router is usually the default gateway for that client. So whenever that client wants to communicate outside the network, it is going to use this particular IP address. In the previous example over here, when you have this new client connecting to the DHCP, connecting to the network, then you can see that the router interface on this network is 223.1.2.9. So the DHCP server is also going to provide this information to this new client. So it will give the client its new IP address, and it will also tell it that if you want to communicate outside this network, then your default gateway or the first hop router's interface is 223.1.2.9. That is where you need to send the packet so that it can exit the network. It also gives the name and address of the DNS server. Okay. DNS stands for Domain Naming System. We studied it in detail in chapter number 2. The name and address of DNS server is important because whenever you want to connect to the global internet or whenever you want to use DNS services, then you need to be able to connect your computer, or client computer should be able to connect to the local DNS server. So in order to basically connect to the local DNS server, you need the IP address of the DNS server. So the DHCP server will also give this information to the client, that first of all, this is your IP address, this is your default gateway or the first hop router, and secondly, this is your DNS server's IP address. Okay. And this is what you need to basically use whenever you want to use DNS services. And finally, the network mask, okay, indicating the network versus the host portion of the address. So by network mask, we basically mean that once we give out the IP address, we need to mention that we are using /24 as the subnet mask. So the network address for this network that you are connecting to is 223.1.2.0 /24. It basically means the first 24 bits are basically for the network, and the remaining or the last 8 bits are being used to identify the host. So once again, how many pieces of information are we giving to the incoming client? First of all, we are giving it an IP address, okay, through a 4-step process. Secondly, we are giving it the address of the default gateway or the first hop router, which is 223.1.2.9. Thirdly, we are giving it the name of the DNS server, and this is the IP address of the DNS server. Whenever you want to connect to it, you can basically use this DNS server. And then finally, the subnet mask, okay, that this is the subnet mask that we are using on this network, and for this network the subnet mask was /24. Okay, so this is the additional pieces of information that your DHCP is providing to your client to facilitate communication, to make it easy for it to basically send out traffic outside the network, as well as to connect to DNS services whenever needed. So this is your typical example DHCP. Okay, DHCP, by the way, runs up top UDP protocol. Okay, we consider DHCP to be an application layer protocol. Application layer runs on top of transport layer. So at the transport layer you have UDP. Transport layer runs on top of network layer. So on the network layer you have IP. Network layer runs on top of data link, and at the data link layer you have Ethernet. And then finally you have the physical layer for transmission. So over here in this example, your connecting laptop needs its IP address, address of first hop router, and address of the DNS server. Okay, so it is using DHCP. Okay, the DHCP request can be encapsulated, like I explained, inside UDP, which is encapsulated inside IP, and which is encapsulated inside Ethernet or 802.1 Ethernet. The Ethernet frame is broadcast. How is it broadcast? That the destination MAC address is all Fs. Okay. Ethernet MAC address is a 48-bit address. Okay. If you flip all the 48 bits to 1, then if you represent it in hexadecimal format, it will come up with a series of Fs. Okay. If you send out a frame on this particular MAC address or physical address, which is all Fs, this is called a broadcast. Okay. So this is how your incoming client basically sends out a broadcast. It sends out an Ethernet frame to FF all the way, okay, for all your 48 bits. Okay. So when you convert the 48 bits into hexadecimal, this is basically 16. Okay, you get 16 different values, okay, which can take on any value from 0 all the way up onto F. Okay, so 16 Fs are basically your 48 bits, which are all ones. When you use this as the physical address and on the Ethernet layer to basically send out the frame, okay, it will be received by your DHCP server, and then your Ethernet is basically demuxed to IP. It basically means we extract the IP, we extract the UDP from it, and then finally we extract the DHCP. So the layering that we have covered in chapter number 1 and 2 and throughout this particular course, we are going to follow the same principle over here as well. When a new client connects, it is going to send out a broadcast. How is a broadcast sent out? A broadcast is sent out when we have a MAC address or a physical address which is all ones. Okay. MAC address is a 48-bit address. So if you flip all the 48 bits to 1, it is going to become a broadcast address. Another way of representing it is in a hexadecimal format, in which you will have 16 values, all of them F in hexadecimal. Okay. So once you send out something to this particular address, it is basically received by all the systems on that network segment. In this instance, you are sending out a broadcast, a DHCP broadcast. So it is going to be heard by this DHCP server residing on this network, and in response, it is going to reply with the DHCP IP address offer. And then the laptop is again going to broadcast that okay, I am using it. So it is going to accept the offer, and then the server is going to broadcast once again that okay, you are free to use this particular IP address. Okay. So this is the second part of it. Okay, that the DHCP server formulates or creates a DHCP acknowledgement containing the client's IP address and the IP address of the first hop router, okay, as well as the name and IP address of the DNS server. So after the assignment of IP address, this additional information is also sent to that particular client. Okay. And then the encapsulation of DHCP server frame is forwarded to the client, and over there it is de-encapsulated and the relevant information is extracted from the frame. Now the client knows its IP address, name and the IP address of the DNS server and the IP address of the first hop router. Now if you look at the diagram on the left, you can see that the server is actually on top of the router. What the author wants to describe over here is that the DHCP server is basically built into the router. Okay, so there is no need to have an additional dedicated server just for DHCP services on a network. Your high-end routers, even your home broadband routers, they basically have this DHCP software running on its own. Okay, the DHCP server software, so that the router can also work as a DHCP server without requiring a dedicated additional server to be present on the network. The server software is actually embedded or built in the router itself. Okay, so no need for additional hardware. Sometimes the DNS server is also built inside the router, so there is no need for an additional local DNS server, a dedicated server. The DNS server and the DHCP server are basically built in into the router. So IP addresses, again, how to get one? How does the network get the subnet part of IP address? So this is the important bit now. Further to DHCP. So previously in DHCP we were assigning, or your router or DHCP server was assigning IP addresses to the end system. But how do we know what subnetwork we need to provide to this network? Okay, how do we basically design the network or create the IP addresses or IP address ranges for the network? Okay, so that follows a similar process as well, similar to DHCP, that you have a large block of IP addresses, such as the one given in this particular example, which is 200.23.16.0/20. It basically means the first 20 bits are reserved for the network or the subnet, and the remaining 12 bits are basically supposed to be used for the actual hosts. Okay, so this is your block given, or the IP address range given by the internet service provider. Now internet service provider breaks this down into further smaller pieces or smaller ranges and assigns each one of those ranges to different organizations. So for organization 0, it is using 200.23.16.0/23. It basically means that instead of 20, now it has reserved an additional 3 bits, okay, which represent the subnetwork. Okay, and then the remaining bits, which in this particular case is 9 bits, are supposed to be used for the actual hosts within that organization. And the organization is free to use those complete 9 bits or further divide the network by borrowing more from the 9 bits, okay, depending on its own design. Organization 1 uses another one, 200.23.18.0. Organization 2, 200.23.20.0. Finally, organization 7, which is 200.23.30.0. Okay. So each one of these organizations is borrowing 3 additional bits from the host side, okay, from the main ISP block or the range given to the ISP block. And then further in the organization itself, you are free to borrow more bits from the host portion to create further subnetworks according to your own requirements and reduce the number of bits which are assigned to hosts. So this is your example of hierarchical routing that we covered in the previous slide. Organization 0 is 16.0, organization 1 is 18.0, then 20.0, and then 30.0. So you have a particular category of internet service providers which are called fly-by-night internet service providers. Let's say these are the internet service providers which are relying on other internet service providers to sell their services. Okay. And then there are further ISPs. ISPs are us. Okay. Different categories of internet service providers. Some of them have fixed range of IP addresses bought from larger service providers. Some of them keep on reusing the same IP addresses again and again. Okay. For the first example, you can see that 200.23.16.0/23, okay, and 18.0, 20.0, and 30.0 are connected to ISP number 1. Okay. Now if you compress all of these IP address ranges, then you can cover all of them by using one single range of IP addresses, which is 200.23.16.0/20. So you can tell the routers on the internet, on the global internet, that if you have anything or any packet that needs to be sent to this particular IP address range, send it to me and I am going to forward it. So once something arrives for 200.23.16.0/20, it is quickly captured or forwarded to this internet service provider. The internet service provider further checks the IP address and sees whether it belongs to 16.0, 18.0, 20.0, or 30.0. And depending on the actual destination IP address, it is going to forward it to the relevant organization. Or the routers inside this fly-by-night ISP are going to forward it to the relevant organization. What is the advantage of this? The advantage is that you have 7 different organizations on the left side which are using IP address ranges which are let's say continuous. Okay, there is no gap between them. they are one after the other. Okay. All of these IP addresses connect to the same internet service provider. So we can compress it and represent it by a single IP address range, which is 200.23.16.0/20, and we can just put this single entry inside the router, so that the router table or the routing table, or what we call the router forwarding table, okay, traffic forwarding table, instead of having 7 different entries, only has one single entry, which conserves the memory on the router. The routers which are present on the internet, as well as the routers which are present on the fly-by-night ISP side. Okay. So these routers, because they are computers, like I explained earlier, they have limited memory. So if you compress the IP addresses to a single IP address range, and you represent it in such a way that all of this is covered by one single IP address, or maybe more than one IP address, then you can just put that IP address in the routing table, and you can tell the internet that if you have traffic for this particular IP address range, just forward it to fly-by-night ISP, and that is going to conserve the memory on the routing table and make the operation of searching for the actual interface where it needs to be forwarded within the routing table much more quick. Okay. As compared to having a very long or very large forwarding table in which you have to search through and find the destination and then the relevant interface. If you compress the size of the routing table by compressing or putting the IP address ranges intelligently, then you can quickly search for your destination as well as forward the traffic to the relevant interfaces. Second example is for ISPs or us. Similarly, it can have also multiple organizations which are connected to this ISP. All of them basically can be covered by a single IP address range of 199.31.0.0/16. So instead of having multiple different entries in the routing table, you can just put this particular IP address in the routing table, this IP address range, and all the routers on the internet, whenever they want to send something to the organizations which are connected to ISPs or us, simply need to forward it to ISPs or us using this particular single entry. Okay. And then the routers inside ISPs or us can forward it to the relevant subnetwork or to the relevant organization. Okay. So this is what we mean by hierarchical addressing, that we aggregate the routes or compress the routes or compress the IP address range in such a way that whenever we want to put an entry in the routing table, usually one entry is sufficient to send the traffic in a particular direction. Okay. So this is another example, and this particular example builds on ISPs or us as well. Okay. So at the bottom you can see that now you have an address assignment of 200.23.18.0/23, which is for organization number 1 that belongs to ISPs or us. So if somebody on the internet wants to communicate with this organization 1, they can be very specific and they can use 200.23.18.0/23, and the traffic will still come to organization 1. But if you have multiple organizations connected to this ISPs or us, then instead of putting an entry for each one of them in the routers in the internet, you can basically use something like 199.31.0.0/16, which is going to cover the entire IP address range for all the organizations which are connected to ISPs or us. So whenever somebody from the internet wants to send something, one single entry is going to be sufficient to cover all of these organizations, and the packet can easily arrive at ISPs or us. Then the routers inside ISPs or us are going to figure out which particular organization or subnetwork this packet needs to be forwarded to. A few last word, how does an ISP get block of addresses? So this particular address that we have been talking about, the very first one, the ISP block, which was 200.23.16.0/20, this IP address range is available for this internet service provider so that it can easily assign it subnetworks from this block to multiple organizations. But where does the ISP get this particular range from? It gets it from ICANN. Okay, ICANN stands for Internet Corporation for Assigned Names and Numbers. It allocates the IP address ranges to particular organizations or service providers, let's say. It manages the DNS services as well to a certain extent, and it can also assign domain names and resolve any disputes regarding the names, domain names, as well as any duplication of IP addresses on the internet. Okay. So this was your video or lecture, which was second part of section 4.4 from chapter number 4, and in this we covered DHCP and hierarchical address assignment in detail. Now in the next part, which is going to be the final part on section 4.4, we are going to discuss network address translation or NAT in a lot more detail. Thank you.